Today we are refreshing our memory of basic concepts of probability. 4. So some key terms that you'll see a lot of: an event, that is an outcome from a particular experiment. And of course, experiment is the process in which you get an outcome. So the experiment would be rolling a die. The event would be to get a 6, okay? The experiment would be collecting students' GPAs, and the event would be to see who has a 3.0 or better. When you look at all the different outcomes and then the outcomes of your event, you're able to create your probability, which essentially is how you go about figuring out the probability of an event happening. It is the number of ways event A can occur over the total number of possible outcomes. So if I roll a die, how many possible outcomes could I have?
6.
I could have 6. And then if I am rolling a die to see the probability of getting an even number, how many ways can I get an even number? 3. So then 3 over 6, which would be 1/2. Okay. If the probability of an event is P in N trials, then you would expect the event to occur N times P times. That is expected value, expectation. When you take your number of trials, rolling a die 10 times, and the probability getting an even number, 1/2, you would multiply them together. 10 times 1/2, you're expected to get an even number, 5 out of those 10 times. Also, do not forget about this symbol, not to be confused with that same apostrophe when it's implied with a function. What does this mean when you see it with the function? Oh, not inverse. Inverse is the negative. The derivative. So that apostrophe with a function means derivative, but that apostrophe with an event is indicative of the complement of a particular event. Remember, complement basically means not. So if event A is rolling a die to get a 6, then the complement of that would be rolling an event to not get a 6. Complements and their actual event always add up to equal 1. And you can always find the complement by doing 1 minus the probability of the event actually happening. All right. The addition rule, also known as the combined events, and I think that's actually how it's written in your reference booklet, which says that the union between A and B is equal to the probability of A, this entire event, plus the probability of B minus the intersection. Because if you count the probability of A and the probability of B, you are essentially counting that intersection twice. And so you want to make sure that you subtract that intersection to get the union. Okay? So the probability of A intersection B is that inside area, and then the union is what you see shaded in yellow. Hopefully you guys haven't forgotten about this. This diagram is called a what? Somebody online? Remember, with any Venn diagrams, because that's what this diagram is called, you need to make sure you have that rectangle around the circles. Without it, it is not a correct Venn diagram, because that box represents your universal set, and you always need to make sure that you indicate it as such. Mutually exclusive events. This is when the likelihood of 2 events happening at the same time is not possible. So then that means that the intersection between 2 events is equal to 0, and the union between them is equal to the probability of A plus the probability of B. Okay, I believe both of these are in your reference booklet. Here is an example. The probability of you picking a card that's an ace and a king at the same time is not possible. It's either going to be an ace or it's going to be a king, but it's not going to be an ace and a king. Remember, intersection uses the word and, whereas union uses the word, anyone remember? Or. Good, just like complement means not. So when you know you're asked those different questions and it's more like an application type problem, you need to know that if it says ace and king, they mean the intersection between the two. And speaking of cards,
Is there a box around there?
yes, there should be if we are looking at a set. And since we are talking about cards, how many cards are in a deck? 52. How many suits are in a deck? 4. How many cards are in each suit? 13. And how many face cards are in each suit?
4 to count those.
But they don't. So it's only 3. Ace is not considered a face card. That's like one of those common things that you would need to know in IB, just like your days of the month. Okay, real quick, how many days are in January?
31.
We just passed through January. How many days are in February?
20.
Because they do not consider leap years. There's only 365 days in IB. Okay, even though we're in a leap, we're in a leap year this year, I think. So there's 29 days this February, but not in IB. Only goes 28. How many days are in March?
31.
31. April,
30.
May,
31.
and June.
30.
All right, online, y'all got the back half of the year. How many are in July?
Yeah.
31.
I'll do that too.
August,
That's what I have to do.
What do y'all do?
31.
September.
That's 31, and then like below
30.
is like.
All right, let's mix it up because I know Kaylee answered those last 3, so let me get somebody different. October, everybody should know October.
31.
There we go. What about November though?
30.
Good. And December, everybody should know December.
30.
Whoa.
1.
31. 31. All right, because like really and truly, they might say like, find the probability or find the expected value or the expected number of days it should rain in January. You got to know that January got 31 days. Okay, so these are things that IB's expecting you to know, but also y'all should know this. Something should be known. 30 days in December. Get out of here. All right, the product rule, also known as independent events, essentially says that the intersection between A and B is equal to the probability of A happening times the probability of B happening. Essentially what that means is that if you're looking at independent events where the outcome of one thing has no effect on the outcome of the other, then you're going to multiply them. So if I roll a die and I roll it twice, the outcome of rolling it the first time has no effect on the outcome of the second time. So if I want to find the probability of rolling 2 6s, well, probability of rolling a 6 the first time times the probability of rolling a 6 the second time, then I multiply them together. So I have a 1 out of 36 chance of getting a 6 twice. Conditional probability is something that we also talked about. If you are doing a probability in your IA, you might want to consider thinking about conditional probability. That's when one outcome is dependent on the other, such as if I am trying to find the probability of selecting a student from this class that has a birthday in April, I'm not taking into consideration the rest of the high school. I'm only looking at this class. So the outcome is going to be dependent on just picking out of this class. Anybody got a birthday in April? I'm the only one? Okay. So it'll be 1 out of 20. The symbol for conditional probability is a vertical bar. That vertical bar indicates conditional probability. So do the words given that, or such that. Another common thing is the word if. So if a student is chosen from this class, it indicates the condition. We're only looking at this class and not the whole school. All right, the formula is the intersection between A and B divided by the probability of it coming strictly from B. B is the condition. And so whatever situations follows those words, given that, such that, if, that is the back part of the formula, that is the denominator of the formula. Last but not least, the different ways outside of a Venn diagram that you can represent information. You have your tree diagrams and your sample spaces. This right here is a sample space. It essentially represents all the different outcomes that can happen if, for example, you throw a die on your first throw and your second throw. These are all the different outcomes. So it's an easy way for you to look at it and then, of course, answer different questions based off of it. Tree diagrams, very common. I would say tree diagrams are probably the most used diagram when it comes to probability in IB, followed by Venn diagrams, and then everything else kind of falls underneath that. So you definitely want to make sure that you know how to work with tree diagrams. Of course, it always starts out with some central point, and then it branches off. Your different probabilities are always along your branches, and your branches always add up to equal 1. Okay? So let's say a couple is having a kid, you know, they have a boy, you know, they have a 1 out of 2 chance of having a boy or a girl every time, okay? They got a 50-50 chance, a 50-50 chance. The probability that they'll have 3 boys, the probability that they'll have 3 boys, and actually, let me fix this Venn diagram some. Because this represents their first child, their second child, their third child. What's the probability on this top branch and the bottom? Very good. And so what's the probability of having 3 boys? 1 out of 8. Because whenever you go along the branches, boy to boy to boy, you multiply along the branches. What about the probability of having a girl? All girls. What's the probability of having 3 children of the same gender? What's the probability of having 3 children all the same gender? It would be 1/4, because you take the 2 probabilities of having all boys and all girls and you add them together. And that's how you get 1/4. So anytime you go along the branches, you multiply, but if you have to take into consideration 2 different outcomes and 3 different outcomes from your tree diagram, you add. Okay? And that's a tree diagram. I have 52 cards in a deck. 1 is drawn at random. What's the probability that I have an ace of hearts? It is 1/52. This is an example of basic probability, okay? The number of different ways that this event can happen is 1 time, because there's only 1 ace of hearts, over the total number of outcomes. You got 52 cards, so that is going to be 1/52. Always make sure that you reduce your fractions. Over here, looking at this one, online, I got 52 cards. 1 is drawn at random. What's the probability that it is not a face card? What is the probability that is not a face card? Yes, it would be 40/52, but we want to make sure that we reduce our fractions. So what number goes into 40? It also goes into 52. Still online?
It reduces
Yes.
to 10/13.
13. I think you got cut off a little bit, but yes, it'll reduce down to 10 over 13. Good stuff, good stuff. All right, let's take a look at this one. Back to online, this one's y'all's. I have two events, M and N, such that the probability of N is 1/5, probability of M is 1/10, and the probability of N union M is 3/10. Are these two events mutually exclusive? All right, Kendall, go ahead.
They aren't mutually exclusive because the union doesn't equal the sum.
Exactly. Remember, to be mutually exclusive, the union should equal the sum between the two. And if we add 1/5 and 1/10, ooh, yes. So this is interesting. Let's talk about this just a little bit, because in IB, they're never just going to ask you, are they mutually exclusive? They're going to ask you to justify your answer. So here, what she said when she said that the union doesn't equal the sum, this right here, if this was written out, the reasoning point would be received. The explanation has been justified. However, by her saying, no, they're not mutually exclusive, she wouldn't get her accuracy point. But that's okay, because out of the possibility of getting 2 points, you still got 1 because you had the correct formula, okay? It would just be that the explanation between the two, or the number part, wouldn't necessarily be correct, because 1/5 and 1/10 actually adds up to be 3/10, and that is what the union equals, so they actually are mutually exclusive. It's okay. Online, I got 52 cards, one's drawn at random. What is the probability that I draw an ace of hearts or any spade? 52. I have one ace of hearts. I got 13 spades. So that is a total of 14 over 52, which does reduce down to be 7 over 26. Okay. Have we banged out all the easy ones? Let's see. Nope. Not yet. Classroom. Chips with integers 1 through 20 inclusive. What does inclusive mean?
Include 20 and 20.
It includes 1 and 20. Are in a box and one chip is picked at random. What's the probability the number drawn is a multiple of 3? Okay. So we know that there's 6 multiples of 3. There's a total of 20. So then that reduces down to 3 over 10. Very good. What does multiple mean? Times by 3. So that will be 3, 6, 9, 12, 15, and 18. Another chip problem. Another chip. Oh, y'all, we all above or below? Okay, online, back to y'all.
No,
Look.
we were 1 through 3.
Oh, yeah, no, y'all are 1 through 3.
Oh, we are?
Oh, okay. My bad. No, not online. It's classroom.
Then it's 1/4.
1/4.
Jeez, I have it so.
5 over 20.
Because it's 5 over 20. That reduces down to 1/4.
It says.
Ooh.
Oh. It's only
Oh.
3/4.
So it's 3/4. This is the probability that it is a multiple. So we want the complement. So the probability of it not being a multiple is 1 minus 1/4, which is 3/4. Ooh, that was quick on that one. Oh, yes. Here we go. Who gets this one? Yes. You say y'all are below?
Yeah.
Online, this one's y'all.
I did the addition rule and then just plugged it all in and solved for probability of B.
Very good. Exactly. Use that addition rule, which says
Yes, ma'am.
probability of A plus the probability of B minus the intersection. And so I'm going to go ahead and erase the union. part and replace that with 4/5. Very good. And then it's just a matter of getting some like terms. But yes, the probability of B is equal to 7/20. Very nice. Very nice. How'd you know it was 5/12?
The flip a coin one was 1/2, and then times it by 5/6
Why am I multiplying?
because that's the intersection
It is the intersection. These are
of independent events.
exactly very nice. Okay,
I do what I don't.
we'll keep working out. Describe how you got 3/10.
So there's 12 doing both. That is the intersection, and conditional is intersection over the condition, and the condition is good that they're doing math, so that's 40.
Good. So we got 12/40, and then of course that does reduce down to be 3/10. Good stuff. Okay. Remember, anytime it follows the words given that, doing math was your condition. That's why I was in the denominator. There were 12 that did both. So you wanted both physics and math, and that's why it was 12 on the top. But is doing physics and math, are they independent? Who said that? Okay. You said no. Well, let's justify. What does it mean to be independent?
I would switch them, the upside down.
Intersection.
The intersection
Mhm.
equal the probability of the first one times the second one.
Mm-hmm. So looking for the intersection of the first times the second. Well, we know the intersection is with the ones that were doing both, right? That's 12 out of how many? 100. How many did math? 40. How many did physics? Out of? What's 40 times 30? Or better yet, what's 4 times 3? Over. They are. So if you have the formula down that justifies it, that you know that you need to use independent events and the correct formula, you just gotta make sure that that follows it. And the one thing too, and I remember this very distinctly from last year, a lot of you guys would just put the numerators. It is the probability. It's the probability of the events. So you need to have it as a fraction or the decimal equivalent, okay? Make sure it's a fraction. Make sure that it represents probability. For this one, the probability that Andrea passed her French exam is 4/5. The probability she passes her math exam is 9/10. How'd you get that?
Well, it says passes both exams, so that would be the U, the upside down U.
Intersection.
Intersection, so then you just multiply them.
Exactly. And we multiply them because they're what type of events? Independent. So we get 36/50, which reduces down to 18/25. Wonderful, wonderful. Then we have to copy and complete this tree diagram. Clearly, I'm not going to copy this because, I write big, I only have so much space. But if it ever says to copy anything, you make sure that you copy whatever it is and then fill it in. Do not be tempted to fill it in on the actual diagram to provide. You make sure you copy because you won't get any points. IB had like slick ways of trying to knock you down points with the rounded penalty, the unit penalty, the financial penalty, not copying and completing. Okay, so make sure that you do what they say. So online, this one's for y'all. My top branch, the one that passes French.
4/5.
405, and Olivia, give me the bottom one too.
1/5.
Very good. Because remember, your branches have to add up to equal one whole. So then let me get somebody different for over here that passes math, fails math. So only 2 of y'all left.
9/10.
I got 9/10 for passes, yes, and what about fail?
1/10.
Good stuff. All right, so Brock, that leaves you with the bottom. That leaves you with the bottom. It is completely blank, so you gotta tell me what goes on the top part and the bottom part and the braces. So there we go, we got the rest of the tree diagram, okay? Passes and fails math or passes and fails French. Now what's the probability that she only passes one exam, but fails the other?
Yeah.
You said 13 over 15? Oh, 15. I thought you said 15. 15. Okay, well, how'd you get that? Yes.
So, let's say she passed French, so she 4 out of 5, and then fails math, so times 4 out of 10.
Mm-hmm.
And then you add that with, if she fails French, so 1/5, and then passes math, so times 10.
And then that's exactly how you get 13 over 50. Wonderful, wonderful. And that's basic probability.